opposed to lilac valves are closed. Teammates are Chris Jenkins, Chris Burns, myself, and Snyder. And outline our system overview. We're going to review previous work. We're going to look at some root locus modeling, PI control results, and then I'll draw some conclusions. System overview, you got your flow transmitter, this is the signal to the flow controller, this is the signal to the flow control valve and that control system. And you can see MV302 and MV303 are open for us. Here's a block diagram, input, output. Our operating range divided into 3 sections, 50 to 67%, 67 to 84, 84 to 100%. We also did another part of it with 50 to 100%. Review, this is our maximum output, 17.25 pounds per minute. Skip ahead.
Go ahead.
Alright. Yeah. Bodie.
Oh, background. Oh.
Alright, Bodie graph. Yeah, this is our Bodie graph. Review of root locus. This is, as you can see, our critically damped. Proportional controller model results. Response to change in input. Our ultimate KCU is 25%. Quarter decay is 16 pounds pound minute per percent. Tenth decay is 12 pounds per minute per percent. And 500, 4.3. Critical damp is 0.36. Pretty sure this is for the whole range, 50 to 100%. Proportional controller model. Looking here, you can see the KC is 25 pounds mass per percent, which is just kind of what we're working. Another one, KC is 16. This is, I think, quarter decay. That one must have been. And proportional only modeling. This is for conclusion for proportional only modeling is not great with experiments. Critically damped model is 0.36 pounds per minute per percent. Critically damped experiment is 4.3 pounds per minute per percent. And here's our PI design parameters. For 50 to 67%, our K is 0.11, tau is 0.91 seconds, P naught 0.57, tau I is 2 seconds. 67 to 84, 0.11, 0.7, 0.6, and 8. 84 to 100, 0.23, 1.9, 0.63, 5. And here's our PI root locus model. You can see A, B, C, and D, and E, which will be shown later on in the charts. The root locus modeling, that's 50 to 67%. PI root locus modeling, same thing, but we actually have the values in here. Our over damped is 0.31, or critically damped 0.44, 12, 16, and 24 is our ultimate. KC results. I just showed you the 67 to 84, that 24, and then our other values. Ultimate range is 33, 24, 21, and 27 for the whole thing. And quarter decay ranges from 12 to 23. 10th decay ranges from 8.7 to 18. And 1/500th decay ranges from 2.4 to 7.8. Comparison of your root locus for proportional integral. As you can see, the ranges of 50 to 67% have higher KC values almost all the way across the board than everything else. The 50 to 100% is second highest usually, and that might be influenced by that first range of 50 to 67% that does pick that up. And as you can see, they're pretty consistent throughout. So the root locus modeling, it was consistent, that's what I'll tell you at this point. Our experimental PI proportional integral result for that range are 50 to 67%. Ultimate's 34. And our critical damp goes all the way down to 2.1. Oscillatory long time. Here's a comparison of decay ratios from experimental to root locus. As you can see, our experimental data has higher decay ratios than predicted from root locus. So root locus is proven to be an inaccurate assumption or inaccurate prediction. 67 and 84. As you can see, KC ranges from 0.36 to 25. And again, we have the same type of chart where the experimental decay ratio is higher than our predicted from root locus. So it's consistently inaccurate. 84 to 100%, same thing. Critical damp is 1.4. Ultimate KC is 0.1. And here you can see this value right here is your, I think, your core decay, and it it's off. That was actually that range didn't work out quite well, but it still shows the same trend where your experimental K ratio is higher than your predicted K ratio. And here's for the whole range. Probably gonna be the same. Experimental higher than and disturbance. And how we're going to create a disturbance by opening the wash valves in 30 seconds. So basically we're doing the experiment like lilac would and have the wash valves closed, but at 30 seconds we're opening. And KC for the results we're using 17 for KC. Here's our disturbance. As you can see, when the wash valves are open, the system calms down a lot. So by opening the wash valves, we go from ultimate to maybe critically damped, or that might be quarter K.
So that's closed up until...
Closed up into 30 seconds, and then you have a dead time like this. All down in 30 seconds. Reset wind up. You can see that...
red tape is always valves open, right?
Yeah.
All valves open, which is the situation on the right-hand side of this graph, am I right?
Yes.
And the point that we can see here is if those valves get closed, the same PI controller that works fine when the valves are open goes bananas. So that's something to think about if you have how you're going to choose your parameters so that for a disturbance, bad things don't happen. Because if it works fine when the valves are open and then all of a sudden your boss comes by and says, oh, you need to shut down this, and it starts going, woo, 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 your boss might say, I don't like that. Huh?
You're fine.
Yeah, you're fine.
All right. Reset wind up. You can see we use a KC for critical decay, critically damped, I should say. Not critical decay. And it's for reset wind up from 50 to 100%. As you can see, it operates, it has a large dead time, and operates pretty smooth. So, I mean, it is critically damped. And reset wind down, same deal. Operates pretty smooth, but it is critically damped. And percent error comparison. This is that one I pointed out earlier, that the 1/500 tall green bar. That was the one for the 84 to 100% range that was way off. And that's why you see that large error. But for the most part, our errors are consistent throughout. Conclusions: root locus using KC parameters is inaccurate in terms of K ratio, but it does consistently predict the same type of values except for that one. Percent error analysis shows consistency. And disturbance shows that the opening of the wash valves causes the system to calm down.